At the end of the first half of this video lecture, I posed this question to you, where you were pushing a box at a constant velocity across a floor, and I asked you what the rate of change of momentum of the box is. And I sort of tried to fool you by pointing out that you are pushing. And what you already know, if you're doing this through Moodle, is that the rate of change of momentum is 0. Note, the box is moving with constant velocity, and its inertia certainly isn't changing, and so its momentum isn't changing. So the rate of change of momentum is 0. But you are exerting a force on the box, and we've defined force as the rate of change of momentum. The reason this can happen is that the force you are exerting on the box isn't the only force exerted on it. So you're pushing forward on the box, but the box is also interacting with the floor. And you probably know, if you think about it for a moment, that there will be a frictional force back on the box due to the floor. The fact that the box is moving at constant velocity tells us that the strength of these two forces, the one that you're exerting on the box and the one that the floor is exerting on the box, must be equal. And so the vector sum of the forces is 0, and that's why the rate of change of the momentum is 0. You could, of course, push harder. And what you would expect, and you'd be right, is that if you push harder, the box is going to start speeding up. In other words, its rate of change of momentum is going to be a vector pointing forward. Now, the vector sum looks like this, with the big forward-pointing vector by u, the smaller backward-pointing vector due to the floor pointing back, and the vector sum here pointing forward. Or, of course, you could push less hard. Now the box will slow down, and the vector sum of forces points back. What this shows us is that our definition of force as the rate of change of the object's momentum isn't quite good enough. It's fine when we have a situation where there's only one force acting on the object that matters. But as soon as there's more than one, we need the vector sum of the forces, not just one force. And so our definition is that the vector sum of all the forces exerted on an object equals the rate of change of the object's momentum with respect to time. This means we can set up situations where we know there's only one force that matters acting on an object, and we can measure its rate of change of momentum and use that as a measurement of the force. But in most situations, objects have more than one force acting on them that are causing the rate of change of momentum. I've already stated that forces always come in pairs, and this is related to the fact that interactions are always between pairs of objects. But let's see how experiment shows us this, because it also shows something else to us about these pairs of forces. So let's think of our usual situation of two carts colliding. And if we just multiply the Vx by t graph by each of the inertias, we get our momentum versus time graph. And we've already seen that interactions conserve momentum. And the way that plays out is that the change in momentum of the one object is always just the negative of the change in the momentum of the other object. So this is just conservation of momentum, and we've seen this plenty of times. So let's look at it in this experiment, where a fairly soft spring has been used as the interaction between the two carts. And so there is some time for the collision to take place, in this case about 0.25 seconds. We can now use our definition of force. In this case, there's only one force that matters on these carts. And so we can find the average force that this spring is exerting on the carts by just doing a change in P over a change in T, right? That is a rate of change of the momentum. Well, if you just plug these numbers through, you find that the force that cart B is exerting on cart A must be 1.1 kilogram meters per second squared in the negative x direction. And the force by A on B must be exactly the same magnitude, pointing in the other direction. Well, that exactly the same magnitude isn't a coincidence. Let's think about a stiffer spring. So the collision is going to be exactly the same, other than that the soft spring has been replaced with a stiffer one. So in particular, the inertias of these carts are the same, and their initial velocities were the same. Well, we still have to conserve momentum, and if you look, these collisions have been elastic, so I'm going to leave it elastic, and so we have to have the same final velocities. So the only difference is going to be the time for the collision to take place. And so our Vx versus t graph would look like this, where if you compare that with the previous one, the initial and final velocities of the carts are identical. All that's happened is that the collision time has reduced. And again, we can convert that into a momentum versus time graph, and we see the same changes in momentum as before. They come out exactly the same. They have to, because for this elastic collision, there's only one way those delta p's can come out. So the difference now is that the time of the collision is shorter. And so again, using our definition of force as rate of change of momentum, we get the force by B on A as now -3 kilogram meters per second squared, and the force by A on B as 3 kilogram meters per second squared. So they're about 3 times what they were with the soft spring, and that's because the time for the collision was cut in about 1/3. And again, we see that the force that one object exerts on the other is equal in magnitude to its partner in this interaction, and that they act in opposite directions. This is a law. Whenever two objects interact, they exert forces on each other that are equal in magnitude and opposite in direction. The pair of forces that you get out of a single interaction are called an interaction pair. So we've seen examples of this. When you hit the mattress, the mattress exerted a force on you, which is what brought you to rest, and you exerted a force on the mattress, which compressed it. And what we've just seen is that these two forces must be in opposite directions and must be of the same magnitude. But the other thing to realize about interaction pairs that's always true is that they always act on two different objects. In this example, one of these forces is a force that the mattress exerts on you, whereas the other one is a force that you exert on the mattress. So let's check your understanding using a classic thing to get students to think about. Here is a car pushing a truck which is broken down, and they're both speeding up as shown in the diagram. So the car must be pushing on the truck, and the truck, since it's in contact with the car, must be pushing on the car as well. Which of those two forces is bigger?